I got really nervous earlier on other meetings because they mentioned low-cost 3D printing using mobile device as a scanning device, and I was like, wow, this is very highly overlay on my kind of research area. But it's also really good to know that people are trying all sort of different approach, which is kind of like the whole like what I try to do. I think I got a bit echo.
Sounds like the meeting is live.
Yes,
Yeah.
the meeting is now live, so we can get started.
Get started.
Great.
Okay. So
Thank you.
I'll just say a quick word, and then Kai, if you could also introduce yourself for people who don't know you, that'd be great. So this is the Bionic Design Forum. We run this every month, and the topics are in bionic design, or it could be broader than that. So this week we have Kai Shu from Northumbria University in the UK, and very grateful to you here, Kai. So please go ahead.
Thank you. My name is Kai, and I am a PhD student in the field of industrial design. So I'm not an engineer nor a prosthetics, but what we're trying to do with my research is looking into how those experimental prototyping can help people from very different disciplines to bring their best practice from their given field to a field that wasn't really used to that kind of like a technology. As you can see in prosthetics through my past 3 years study, it's a very interdisciplinary challenge, like you require from the designing of a prosthetic device to fitting to the maintenance. It's a very multidisciplinary challenge, and that's why I think it requires a multidisciplinary solution. And my today's presentation is something I did as part of my PhD. Is aiming to solve some of the common challenges when printing prosthetic sockets using low-cost 3D printing device. And my hope is to try to solve them from different angles, from a hardware perspective, as well as from a software optimization. I shared some of the work in our April design meetings, and today is more a update since the product similarly it's past the feasibility stage, but there's a lot of work to do, and get a bit nervous. I think I don't think I can share the screen yet. It's disabled by the host. When we get that sorted,
Hi, I'm giving you host powers right now.
Okay, thank you. I might need to rejoin the meeting if my computer didn't give me permission, because I just installed Zoom.
You have permission now.
Okay. Oh, it works. Great. Let me see this one. Okay. So this is the presentation slides that I post this entire presentation on the e-NABLE Hub. So if you can make it to the meetings, they're also there. And hello, everyone. In this video or in the presentation, I will be sharing 2 experimental techniques I explored during my PhD research. Let's turn on my camera. No, that's too big. Sorry. Just going to turn that off. It's in a different angle. So both of the work I try to share today are designed to address some challenges associated with 3D printing prosthetics, socket using cost-effective FDM printers. And the first technique aims to enhance the efficiency, speed, and quality of the printing through hardware modification. And the second one is focused more on optimizing the socket design process without altering the external shapes. So this will keep its compatibility to its original design accessories by leveraging finite element analysis. And I'd like to start with a bit like a disclaimer-ish. Coming from a design background, I have been really interested into integrating experimental prototyping as a methodological framework for fostering interdisciplinary collaboration. And while I don't have any formal training in mechanical or software engineering, the example I present today may not represent the most optimal approach. It's more a conversation starter rather than a how-to guide. It's there to trying to see like this is why I did, and maybe someone else who might be useful and bring more of their special like field of the practice into it. And I'm eager to hear any suggestions, recommendations, and any challenges you might encounter when you're trying those approach. So let's begin with the hardware approach. So despite the differences in the loading condition, both 3D printed upper line prosthetics and lower line prosthetic sockets, these are shared challenges. It's when you want to print them like without any support material, the sockets usually need to be printed oriented upright, it's like in an upright position. This is allowing the flat socket adapter to be printed first, followed by the rest of the sockets. However, like there's a lot of researchers have observed a mechanical failure between the interbond layers between each individual layers. And some believe this is caused by the relative load-bearing surfaces has been reduced, and the reduction in relative load-bearing area in the interface bond and a filament scale. And I believe it's classic, and others believe it's due to it's due to factors occur parallel to the printing direction. So what they believe is for the best load-bearing capacity as well as toughness, it would be ideal to orient the sockets in a direction that its most dominant stress, like this one, is parallel to the printing direction, which is the filament deposition directions. And this is basically what I'm trying to achieve. But printing in this configuration isn't always feasible for a lot of 3D printer, regardless like it's a low cost Industry Pro or high-end printer, because the print volume is usually very restrained. And printing in this manner also require a lot of support material, especially inside, which also might increase adding additional post-processing steps compared to the upper configuration, leading to more labor cost. So what I did is I modified this under 3 Pro, and I introduced a rotating X. I termed this RX. This allows socket to rotate around the RX. Meanwhile, the printer tool had moved exclusively along the XZ plane and completely bypass any YX movements. This is for two main reasons. First is this will deposit material in the direction that's parallel to the most dominant stress, specifically along the X or the RX. And the second one is that, as you can see, the support at the platform is already mimicking the residual length. So this minimizes the requirement for supporting material during the printing process. I will explain the support platform later. So to implement this modification, I first started by removing the original whole bed assembly from the Creative Pro and the 3 Pro. And then I repositioned the Y-axis stepper motor. Instead of its origin function, now it's driven a road that's supporting the new build platform. For this, and this is how it looks. So to make this actually work, because you can't use print on the road, I designed this what I called a build platform adapter, and this is printed. This is a 3D printed model, but ideally this should be like when up to scale. This should be a custom model from the user studio them, and this will ensure a precise fit. And this is also designed to be like a kind of like a reusable part of the whole system. Like you can put this adapter back on and print a new sockets or repair the old sockets. And this is what it looks like with the build platform adapter installed. So in this very early, this is like one of the very early tests. You can tell probably by I have a lot of blue tag there as mounting mechanisms. Controlling a modified motion system like this isn't very straightforward. It's a standardized standard slicing software. So I also developed a custom slicer using Grasshopper to accommodate the modifications. The slicer is basically first able let the machine understand like there is a build platform there now, and the system recognizes that it's there. It can print on the adapter, but must avoid moving into it. This is done by the machine will generating what I called a safe work area. This is a designated region where the tool head is permitted to move around. And for that, we load the socket, which is the right part on the screen. And for any given rotation angle, the slicer will calculate what's going to be printed within the designated work area. This is done by calculating the intersection between the safe work area and the socket at a given point. And from there, the slicer generating a tool path from the starting from the very bottom layer all the way to the top, and on also each rotating angle. And you can see that the tool path is very simultaneously attached to the platform adapter. At the same time, the slicer also need to do some essential housekeeping calculations, things like how much y-axis travels equal to 1 degree or a given degree value, rotation degree values, as well as like calculating the extrusion value based on flow rate, nozzle size, layer height, and filament size. So, and when that all completes, we're generating the G code with other command like G1 to instruct the print head to go to certain directions, and things like that. While this modification shows promises, there's still a lot of work to be done, both on the hardware and the setting software front. For instance, it's like the auto homing features, like there's documented a manual homing steps. Basically, you need to manually move the tool head to a manually defined origin position. And also, additionally, a quick release mechanism instead of blue tag will be nice for detaching and attaching of the build platform adapter. And essential functions such as like filament retention will be also be added, as you can see, through strain artifacts on the print. But at this stage, I feel confident this is like this modification, because it's demonstrating the possibility, is enough to show this can work. With a more experienced engineer, I believe we can construct something like a machine that's specifically designed for socket printing, only using cost-effective components. And this is kind of like what my research is about. Like my primary goal is to explore the potential of such systems. And if it's been proven effective, perhaps a more experienced engineer could refine into let's say a household item that people don't need to know how to use a computer to operate on with. We can like install a time-of-flight sensor on the tool head. Then this will be able to scan a new build platform. Like if the patients have evolving residual limbs needs, they can just using like a cast, like using basket and making a new cast as the build platform adapter. The printer will scan the new adapter and adapting the socket printer upon. By having a TOF sensor also will enable something like maybe repair printing. If part of the socket is damaged, instead of printing a new one, the printer is capable to just print over the damaged area. And the overarching vision is to foster interdisciplinary collaboration, potentially integrating mature practice from other disciplines, like something they already use very well, but it was still very new concept in the specifics field, and putting them into a prototype and assessing how that will impact the 3D printing prosthetic domain. And that's the hardware part of my presentation. And I will move to the software development part, because that's software optimization part, because that's a very short part compared to this hardware work I did. And then if I don't have any questions, I will answer them in the end. And this is what I did with the software, some design optimization I implemented with the 3D printing sockets using finite element analysis. I began with this huge workflow by using 3D scanning to create a model of a residual limbs from this generated socket, which I termed it the baseline socket. And then I run a simulation on this baseline socket, apply an artificial defined external load to mimic the daily usage of the socket, like the wear or carrying things. And this simulation produced a mesh model that's highlighting the region on the socket where it's under the most stress. I named this mesh model the high stress area. During slicing, which is like how the software that prepared the design file to be printed, the high stress area is then used as a infill modifier. This will allow for adjustments in the infill density of the high stress area, while the rest of the model remain unchanged. The reason I choose to focus on the infill rather than just the overall geometry is this will first ensure that the original design is maintained, and this preserving the compatibility with other accessories that was designed for the original parts. The second is generative design approach usually generate those really beautiful but very organic geometries. And if you're not printing them with material like resin, or even if you print with resin, you realize it's very hard to post-process something very organic. There'll be small area you can just kind of reach. And that's obviously will increase the cost. And this is my initial setups. I used a Arctic EVA M 3D scanner, I believe. And but the thing is, this scanner isn't very good for what you need to do, because the tracking method is and also the tracking method doesn't really work with the geometry of human arms. There's always loss in track, resulting in a very bad mesh. And considering the cost of that device was about 10 to 15 grand, I later translation into a more budget-friendly solutions. This is a software I believe was under 10 British pound, and is using the iPhone's biometric scanner, the true depth camera, to creating a 3D model, which is actually quite accurate. But back to the original 3D scan. After scanning with the Arctics, I processed the data using this Autodesk Mesh Mixer. From there, I modified my scan to mimic a residual lamp for demonstration purposes. And so here I can start with the socket creation with as if this is a real residual lamp scan. So first, I define a socket area. This is also ensuring like that there is enough rooms for upper movement for the residual lamps, and then I clean up the edges, and like there's settings into also I offset the inner surface to leaving enough space, like you can see, for the socket liner. And following the steps, I offset this socket, generating a body and a smooth edge, like but also like make sure the shape is preserving, so it won't really in the way of like for the arm to bend. And lastly, I added a terminal device adapter to the socket, so this can be attached to other terminal device, either so passive hand or other accessories. However, my initial attempt using ANSYS Mechanical has a lot of challenges. Defining external load conditions with a mesh model with like the 10,000 faces wasn't very feasible. So I had a workaround by using Autodesk Fusion 360 Mesh to solid conversion, which I believe is a paid plugin for their product design subscription. And this did allow the stress simulation to run successfully ANSYS Mechanical, and applied the high stress area, which exploded from on the figure E on the screen right now, as a infill modifier. Then that area, as I believe I defined as 100% infill, while leaving the rest as 10% infill to a baseline socket. And this, if you print the rest of the model clear, this is how it looks like. Like you have some less dense area, and you have the very high dense area, which usually have a higher like responsibility to load bearing. But this approach wasn't very optimal. First, the external load wasn't actually accurately defined in ANSYS. It was more just make sure the workflow was working. And by adding mesh to solid conversion is adding unnecessary complexity and cost. As I said, I believe is a paid plugin for the Autodesk 360. Seems like £400 a year. And so I streamlined the entire process only using SolidWorks. well, I did also use March Mixer, but the part March Mixer was doing is fully doable only in SolidWorks alone as well. Like the scan to 3D plugin offers same functions. I just already did all the pre-processing in the March Mixer, but you can do the entire process now only in SolidWorks. So using SolidWorks, I import the March scan with the scan to 3D plugin, and they have the scan to 3D March preparator. Since I already did most of the the few first steps in March Mixer, so I skipped them here. But if you didn't, you can reorient it. Oh, someone's in the waiting. Let me put them in. Sorry, I didn't realize I'm the host. I hope I didn't let them wait for too long. Hi. Where am I? So in the SolidWorks, I import the March scan using scan to 3D plugin. And as I mentioned, since I already did the pre-preparing in the March Mixer, so I skipped the first few steps. But if you didn't, you can do all of them in SolidWorks alone. Like you can reorient them, remove the unnecessary March, and simplify the overall geometry. And then I make sure you don't cap any holes at this point, and then move to the surface wizard, which I found the most issue I ran into is in these steps. So I opt for the automatic surface creation and retain the default settings. But instead of using the fixture line that was generated by the wizard, for the most optimal result, you want to remove all of them and reconnecting the quarter position on both ends. SolidWorks won't allow you to remove all the fixture line at once. So you probably want to remove 3 of them first, and then add your own, and then remove the last wizard generated one. When you finish, you should have like a very clean surface like the one shown on the right-hand side. And then I use second fixture, generating sockets, and kept the open end for the terminal device. Before moving on to simulation, I reference sketch for the FEA, and on the terminal device surfaces. I save this current stage as the baseline socket, move the entire thing to a simulation workspace, begin by defining the material and constraint of the socket, and then apply some external loads. In this demonstration, I applied one, one second, there's a chat. So in these examples, I applied 100 Newton force in both horizontal and vertical directions, as well as one torque of 10 Newton meters on the central axis. This is to mimicking a daily use to the socket. And with all the conditions set, I initiated a topology study aiming for the best stiffness to weight ratios. My target was for 30% weight reduction, and after running the simulation, I resulting with this model on the far right, the figure F, and I call this the same as the stress area. And this part, in conjunction with the baseline socket, can then be combined together in the slicer and used as a infill modifier, and to perform the infill optimization as demonstrated earlier. And that's basically it. Those are just a few techniques I discovered during my studies, and I think might be beneficial for 3D printing prosthetic sockets. And I do hope offer some fresh insight into your current practice, and perhaps it inspire you to integrate some of your techniques from your own field into the realm of 3D printing prosthetics. And like I said, I'm not expert in either hardware or software engineering. This is really just like show you, hey, I know like this is what I do in 3D print product design. We have those techniques we usually use for designing other objects, but we find this might be useful in the 3D printed prosthetic sockets, and therefore I bring them over to see how this may react. And I believe there will be many other example just like this from other discipline, and only by encouraging this kind of collaboration, I believe we can providing more useful solutions. And thank you. Getting nervous. How do I send? I'm not sure how do I send the host back to you. Lots of remotes.
Hi, that's okay. I'm still
Oh.
the host. You don't have to do
Okay, that's good.
anything. Thank you for your
Sorry, I'm a
presentation.
little nervous. Hi.
I'm sorry I missed the beginning, but I'll catch up on the video. Hello, Vivek. Hello, Kai. That's very, very
Hey.
interesting work that you're doing.
Yeah.
I have a colleague here in Rochester named Kyle Reeser, who did his PhD on rotary 3D printing and will be very interested in what you're doing and comparing notes. He's also now making a bioprinter as a custom product. So he'd be a good contact for you. As soon as I get this video, I'll introduce you to each other. Where are you located?
Newcastle.
Newcastle in England.
It's in Newcastle upon Tyne, yeah. The university is the Northumbria University.
Got it. Great. Nice work.
Thank you. I was kind of worried earlier in the last meeting when he mentioned he's like using iPhone as a scanner, which is actually a very brilliant idea. I can't remember his name from the
Florian.
Florian. Yes. He mentioned he using iPhone as a scanning device for lower line prosthetic sockets fitting in Africa. Also, like the use of low-cost 3D printers within the 1,000 pound range. Which is both something I personally encountered as well, because I began my research by testing the workflow, and I noticed the device we're using, like the 3D scanner, was about 15,000. The printer we have in the lab is about 20,000, and then it's just not very feasible. I mean, it works for testing the workflow, but I know you have to drop down the cost. So eventually, we move on to see if we can do with a iPhone scanner, because to ensure the bio authentication's accuracy, it's actually very good scanners. It's just not as easy to use as those very commercial package, but I'm sure with the help of with a more skillful engineer like they did, we can make it a much easier use interface. I saw someone making a mirror, putting on the top of the iPhone, so they can scan in front of them rather than you don't have to see in the back of the iPhone. And it's just small change like this, I think, gonna be adding together and become paradigm shifting for the field.
Have you looked at his UFit software and compared that?
I did. It looks very promising, because I was thinking about something like using like a Blender, but personally I wasn't that good with Blender. But the thing is like when I bring my work to some local tinker space, not everyone have the same access to software like we have in the university. Like SolidWorks, I don't think it's very budget friendly. I think it's also above 10 grants area. I think the Autodesk set is probably cheaper, around 100 pounds a year, but that's not including any simulation. So if you want to do anything that I propose, like a finite elements analysis based optimization, it's basically very budget friendly. But I did see some works in the simulation space, people using Blender to do a lot of like near topology optimization. I don't have the skill to implementing it, but I think that's one direction people can invest into. Like in my thesis, I described it. This is like the property we have as human muscles. It's called a muscle plasticity. It's we adapting our muscle structure or density due to our daily use. So those numbers might be incorrect, but if I only doing light office work and I never carry any load with my prosthetic device, or with my own hand and arms, I will have less muscle density than let's say a person who need to carry a lot of heavy load every single day. And I think this should reflecting on the 3D printing prosthetics they are using, because this is like just like muscle. If you don't need to carry that much load, you might be benefit for a lighter model, lighter sockets. And there's like a human muscle that if you change the input parameter of the simulation by defining a lower load, your socket maybe is lighter if this one get damaged, or you realize you need a higher loading capacity, you change that parameter. And it's tailoring the sockets into your own needs rather than just having one fit all. Because like for a commercial mass production product, that's kind of the default setting, because there's really not much option when you cast modes of sockets. But for 3D printer, I think that's one of the advantage. We can making very user-specific changes based on their daily activities.
So I hope you can come to next week's town hall meeting, and I would urge you to send your video and an email directly to Florian so that he has a chance to see what you're working on. I heard you say you were nervous. I don't think you have any reason to be nervous, but I do think that there's one thing that Florian has done, which is not common, is that he's managed to put it into practice. We academics, people doing theses, they do this wonderful work, and the result is that they get a degree. And the result is not that people actually get devices. And so talking to him about how to compare notes, how to make sure that the good work that you've done goes forward, I think it may turn out to be an important thing that we can facilitate.
Thank you. Definitely. Where can I find his contact information? Is that going to be on the slides earlier?
I'll bet you I do. I'll check right now. Meanwhile, I want to see if Vivek has any comments or questions. Nice to see you again, Vivek.
Hey, how you doing, John? It's been a while. I'm sorry, I've been remiss in attending. But I do have a question, Kai. So I think the fundamental premise of your work is that you lay down the fibers in the axis of loading, right? Versus doing it transversely. Did I get that right in the first place?
You mean the way I modify the printing, the physical printer?
No. The way you lay down the fiber or the print is in the direction of the load, right?
Oh yes, that was one of the challenge I find throughout the literature regarding like a socket damage and print.
Right.
1 second. This is the one. Yeah. So there was a lot of literature observed that the printing, the filament printing or filament printing direction is getting strong. It's only the strongest when it's parallel to the most dominant stress.
Okay. Yeah. So the question I have is, were you able to validate it with any of the experimental stress tests? Stress to breakage. I think last time we had talked about connecting you with Eric, and Eric is doing some work in this area, looking at load bearing capability or whatever. So I was just curious if you had.
We did considering to implementing some of the tensile testing, see if this actually can produce any measurable like improvement. But it's like as I mentioned in the very beginning, it's like I think there will be a lot of uncontrollable factors because I'm not having the required engineering skills to make sure my other human error won't really affecting the result of this in theory better solutions. And thus we didn't move on that as primary part of our validation. We more think about this as like a way of facilitating like a design workshop, like a design study, this is what can I do as a designer from my field, and those are my field best practice. And then I think those can be brought into the prosthetic field, and what other people can do to bring their best practice from their given field into prosthetics manufacturing. But we do have plans to continue validating with but at the moment we just prepare to let it pass the feasibility study and ask for how much better, how much improvements it will provide. I can't make any promise. That's beyond my scope.
Okay, thanks.
Thank you.
Kai,
Yeah,
I have checked and I don't have Florian's email, but this is the website, as you probably know, and they do have a contact form. If you give me your email, I'll ask Adam to connect you with Florian.
Send you to the chat.
I can also do that too.
All right, then. Even
So-
better. Thank you.
Yeah.
Thank you, Sarah.
So I missed the beginning of your presentation, and you don't have to go over anything you have already. But where do you go now? You've just done this interesting thesis. What happens next?
So I'm moving on to a like organization that's focusing on something similar, like target audience. It's more to do with the aging community, and personally, I think I might pursue to see how I can bring this kind of practice into not just prosthetics, but into like my future works. And my supervisor from my old lab, my previous lab, also have the ideas like how we implementing digital twin technology as well as like Internet of Things. But the thing is like most of my supervisor, their work is not really like to make it happen. More about it's like what he said in his presentation earlier. Like all we do is not really to make everyone have access to like the aesthetics, but we're making it more. It's more like we are more solving like first world problems. That if that's allowed to say, but I'm trying to see if there's any space in this domain that I can bring in impact, such as like I'm encouraging like instead, because we don't have much center in the UK. Like the current situation in the UK is, this might not be incorrect because I haven't fact checked since 2019. But there apparently used to be a huge waiting time for prosthetics to be fitted, and this is due to lack of the resources that allocated into upper limb prosthetics, and it's only getting worse because it's a very uneven issue, which the field calls is the prosthetics dilemma. There's more lower limb prosthetics, lower limb amputee patients than upper limb amputee patients. And the resource is going to be more restrained and the waiting time is going to be longer. So we kind of trying to make like thinking if we can making up sockets to be almost like a home appliance. You can buy it within 200 pounds at home, and you can just update your sockets in overnight to reflect the daily changes and making repairs. This technology maybe will be feasible to replacing the current fitting system, and in long run, because like the technology price is always going to be lower and lower. Maybe we can deploy those things like to where he's working on in Africa, and eventually, because like he said, like it's very hard to ship in there, but we can do. I think there's a lot of opportunity to offset of some of the on-site work to making a lot of things more remote, like you can have people scanning and in a slightly more centralized but high efficiency facility to fabricate or make everything on demand. But like you mentioned, like a lot of those work we do is just thinking but not really taking much into action. So I don't really exactly know where I will be end up in like say 2 or 3 year time. I might not in the field anymore, but I will still trying to do as much more volunteer work as I can. But I will try my best to bring this kind of approach, like decentralized, community-based, open source 3D printing to prosthetics into like any work I'm working on.
That's great. So I think that we should make sure that both Florian and Kyle are familiar with what you're doing, and you should be familiar with what they have done also.
It was very inspiring.
That'd be great. Great.
Thank you.
Do we have any other questions or topics?
Doesn't sound like it.
Okay, I will, you should actually, you can search for Kyle Reeser on the hub, Kai. His name is Kyle Reeser. And I think you'll find some background on his work, but we'll connect you directly. It's very closely related. He didn't do anything on prosthetics at the time, but he did work out a lot of the rotary technology that it sounds like you've been working on also. And we'll see where these conversations go.
That's great. Thank you so much.
Thank you.
Good.
Thank you very much.
Thanks,
I
Kai.
will look later. Yeah, thank you.
Thank you.
Appreciate it. Talk to you later.
Goodbye, everybody. Thank you.
Take care.
Bye.